So I want to talk about Bohr's atomic model. So Bohr also gave his ideas about an atom which he came to understand. So what Bohr said is, when you have got an atom, electrons orbit about the nucleus in circular orbits. So that is one of the postulates of Bohr. Electrons orbit the nucleus in circular orbits. So they orbit in circular orbits. So they orbit the nucleus in circular orbits. That is, they move around in circular orbits by what we call Coulomb's attraction to the nucleus. So we have got a nucleus and we have got shells. So we know that the nucleus has got protons which are positively charged, electrons are negatively charged. So these electrons are able to revolve around the nucleus by Coulomb's attraction to the nucleus. That is, negatively charged electrons will be attracted to the positively charged protons in the nucleus. That is why electrons are not able to slip away from the atom. Alright, so that was one of the ideas or the postulates of Bohr. Another thing that he came to understand is angular momentum is quantized. Okay, orbital angular momentum is quantized. So that is orbital angular momentum is quantized. So the meaning of quantization here is it has own specific values depending on the shell that you are talking about. So the equation relating that is orbital angular momentum is given by energy level times Planck's constant over 2 pi. So Planck's constant is 6.626 times 10 to the power negative 34 joule second. And then we know pi is a constant and n is simply the energy level. So for the first energy level you put 1 there, for the second energy level you put 2 there. So orbital angular momentum is quantized. That means it can only occur in certain values. So if you know the orbital angular momentum for the first energy level, to find the orbital of the orbital angular momentum of the second energy level, just multiply by 2. Third energy level multiply by 3. That is the meaning of quantization. It can only occur in multiples. You can't find it as a fraction or as a decimal of that number. It can only occur as in multiples. Another thing that Bohr came to discover is that electrons in stable orbits do not radiate. So electrons in stable orbits do not radiate. So we can understand radiate as to remove energy. So if an electron is in a stable orbit, let's talk about maybe the ground state of an electron. When an electron is in the first energy level, it is so stable, it doesn't want to move out from there. It is so stable. So because it is stable, just like you and me, when we are stable, we don't want that situation to change. If all is well, we don't want things to become bad. We always want to maintain that situation we are in. But whenever things become bad, we always want to return to a good mood that we had. So electrons in stable orbits do not radiate. They don't want to move from the orbit in which they are. They don't want to step into the next orbit or to go into a lower orbit. They don't want to change energy levels because they are stable. Alright. So another postulate that Bohr came to discover, or the idea that he gave, is that electrons are able to radiate. Alright. So that is, electrons can change orbits if they radiate energy. Orbits if they radiate energy. Let me just say, alright. So electrons can change orbits if they radiate energy. So what are we saying? If you have got an electron, let me just make a draw there. Alright, sorry my drawings might not be to the standard, but hope it helps us. So if you have got this as your atom, let's say this is the nucleus and this is our first shell, n is equal to 1, this is our n is equal to 2. So electrons can change orbits if they radiate energy. Okay, so what if an electron is here, it releases energy, so it has released energy, let's say that is capital E, to differentiate from electron. So when that electron loses energy, now the electron which is in the first energy level can't go anywhere else. Okay, so let's say it is the electron which is in the second energy level that has lost energy. So let's hope there's an electron here, it loses energy. So if it loses energy, it is able to drop to the next energy level, to a lower energy level. Because it has lost energy, the energy will be negative, to mean losing. But an electron which is in a lower energy level, after gaining some energy, so if you project energy on it, so it gains some energy, so because it has gained, the energy will be positive, it is going to go to the next energy level. So electrons are able to change orbits after gaining energy. So we can calculate the energy of an electron in a specific orbit or in a specific energy level, and that will be calculated by the Ryberg equation. So energy is given by negative R Z squared over N squared, where this R we are saying is the Ryberg constant, that is let me just find out the value for R. That is negative 2.178 times 10 to the power negative 18 joules. And then Z is the atomic number. Now because Bohr's model works on an hydrogen atom, an hydrogen atom has got atomic number of 1, so we use 1 over N squared. If not, or the questions will be given will be referring to an hydrogen atom, and so you always use 1 on top there. Alright, so if you want to calculate the energy of an electron in the first orbit, put 1 where there is N. So simply that will be negative 2.178 times 10 to the power negative 18 joules, and then 1 over 1, which will simply be 1, and so the answer will simply be this same one. In the second energy level, we're going to put 2 here and then square it. So it is just this number, we're going to divide it by 4. Third energy level, that will simply be 3 squared. So this number just divide by 9. So that is what we are saying. Energy is quantized. It can only occur in some units. So this is the reference point. Any other will just be a multiple of this. So you just be dividing depending on the energy level that you are talking about. So the energy level you are talking about, square it and then divide by this energy level. That will give you the energy of that energy level we are talking about. Alright, so we can use the same equation to determine the energy change when an electron transitions from one energy level to the other. So the energy change will be given by negative 2.178 times 10 to the power negative 18 joules, and then 1 over N final squared minus 1 over N initial squared. So this first part is simply telling you the energy of the first shell in which the electron was. Sorry, this is final. The energy of the shell in which the electron is going to go minus the energy of the shell from where the electron is coming. That will give you the change in energy that is involved when an electron transitions between two energy levels. Imagine an electron moves from the third energy level to the second energy level, like that. What will be the change in energy? So that will simply be negative 2.178 times 10 to the power negative 18 joules and then 1 over, now this is any final, so it is going to the second energy level, that will be 2 squared, minus 1 over n initial, it is coming from the third energy level, like that. So if we say 1 minus 2 squared, that is 1 over, okay, 1 over 4 minus 1 over 9. That is giving us 5 over 36. Now multiply that number by 2, negative 2.178 by 10 to the power negative 18. So what we are getting is negative 3.025 times 10 to the power negative 19 joules. So this is the energy this is the energy change required for an electron to move from the third energy level to the second energy level. Now the reason as to why it is negative is when you are moving from a higher energy level to a lower energy level, an electron is supposed to lose energy because it's moving to an energy level that has got lower energy. So it has lost this amount of energy for it to drop to the second energy level. Alright. So just as I've said, you need to project energy on an electron which is in a lower energy level for it to move to a higher energy level. And you can calculate the energy of the photon, or what we mean by photon is simply the energy of light which you are projecting on that electron. So imagine you've got these shells, you have got an electron here. So if you project energy on this electron, so this energy will be in form of photons. So photons are simply a unit of energy. So this electron is going to be able to move. Now you can calculate the wavelength at which this photon is, and that wavelength will determine where that shell is going to go. I mean where that electron is going to go, in which shell is going to go. Alright. So let's try, how do you find out that wavelength? So before even calculate that wavelength, we need to understand something which is called the wave number. So wave number given by the symbol that is the reciprocal of the wavelength. So that is the reciprocal of wavelength. So we are saying wave number is 1 over wavelength. So from this we can tell that wavelength is also 1 over wave number because they are reciprocals of each other. So to calculate the wavelength of a photon that is needed to change an electron from one energy level to the other, that will be given by, so we know that wave number, which is 1 over wavelength, will be given by RH. This is the Ryberg constant. So this Ryberg constant is talking about wavelength. On the previous one, we talked about Ryberg constant when we're talking about energy. That is 1 over n final squared minus 1 over n initial squared, where this RH is 1.097 times 10 to the power 7 per meter, and then it will be 1 over n final squared minus 1 over n initial squared. So that is how we do it. So we can calculate the energy, I mean the wavelength of a photon needed to change between energy levels. Let's try to calculate the energy, the wavelength of a photon that is required to remove an electron from n is equal to 3 to n is equal to 2. Alright, so we know that wave number is given by RH 1 over n final squared minus 1 over n initial squared. So RH, we said the Ryberg constant is 1.097 times 10 to the power 7 per meter, and then 1 over, the final is 2, that will be 2 squared, minus the initial where it is coming from is a 3, that will be 3 squared. So that will be 1.0. Okay, let me just do it direct, just multiply direct, so that we don't waste a lot of space. So what you are going, you get first what is in the bracket, that is 1 over 4 minus 1 over 9. That is 5 over 36, and then multiply by 1.097 times 10 to the power 7. So what I'm getting is 1523611.111 per meter, because this is in per meter. Now determining the wavelength. Wavelength, we know that it is 1 over wave number. So that would be 1 over 1523611.111. So taking the inverse of that one, what we are getting is 6.56 times 10 to the power negative 7 meters, which we can convert to nanometers by multiplying by 10 to the power 9, and that will give us 656 nanometers. So that is the wavelength that is required to remove the wavelength of the photon required to remove an electron from n is equal to 3 to n is equal to 2. So the vice versa is also true. If we want to remove an electron, let's talk about from a lower energy level to a higher energy level. What happens when an electron transitions from n is equal to 2 to n is equal to 4? What will be the wavelength of the photon that is going to be taken in? So we know that wave number is given by Ryberg constant 1 over n final squared minus 1 over n initial squared. So that is 1.097. By the way, this constant will be given to us whenever we are solving in the papers. So the final to which is reaching is 4. That will be 4 squared minus where it is coming from is 2. That is 2 squared. So that will give us, so 1 over 4 squared, that is 1 over 16, minus 1 over 2 squared, that is 1 over 4. That is giving us a negative 3 over 16, and then we multiply by 1.097 times 10 to the power 7. Sorry, let me just do that again. Multiplied by 1.097 by 10 to the power 7. So what I'm getting is a negative 2056875 per meter. So I want to calculate the wavelength. Wavelength is 1 over wave number. So that will be 1 over this same thing. Now this negative, you leave it out. So when you are talking about wavelength, there's no way that wavelength can be ever negative. So if you are calculating, you find a negative, you just need to remove that negative. Unless energy, you can keep that negative because it might mean you are losing energy. When it comes to wavelength, just leave it out. So what I'm getting is 4.85 times 10 to the power negative 7 meters, which is 485 nanometers. So that is the wavelength that is involved. So that is how you can calculate the wavelength. You've got the first energy level there, second energy level, you have got the third, the fourth, and the fifth. So whenever an electron is dropping to the first energy level, regardless from where it is coming from, as long as it is dropping to the first energy level, we call it the Lyman series. So we don't care where it is coming from, whether it is coming from n is equal to 5 or wheresoever, as long as it is reached the first energy level, that is the Lyman series. When it drops to the second energy level, regardless from where it is coming from, that is called the Bohr series. And then dropping to n is equal to 3, and we don't care where the electron is coming from, that is called the Persian series. Dropping to the fourth energy level from any other energy level, that is called the bracket series. Now whenever an electron drops to the fifth energy level, it can come from anywhere else, that is called the p-band. So they might ask for the region of the electromagnetic spectrum where the electron will be the photon that will be released will be found. Now see, we are coming from higher energy levels to a lower energy level. We are dropping from n is equal to 2, or from n is equal to 3, or from n is equal to 4 to the first energy level. So it means a photon should be released because we are dropping to a lower energy level. So such a photon which will be released when an electron drops to the first energy level will be in the ultraviolet region of the electromagnetic spectrum. So when it drops to n is equal to 2, it will be in the visible light spectrum. So that photon which will be released. Now for these three, P fan, bracket, and partial, n is equal to 5, n is equal to 4, and n is equal to 3, that will be in the infrared region of the electromagnetic spectrum. So in case they ask, that is what we have. Now another thing maybe we need to understand is the wavelengths, because sometimes they might give you the wavelength and then they ask you to determine the region of the electromagnetic spectrum in which that wavelength is found. So we have got first the gamma rays, we also have the X-rays, we also have the ultraviolet rays, and then we have got the visible light, we have got infrared, microwaves, and also radio waves. So the wavelength for this one is 10 to the power negative 12 meters. So just be reducing by 2 to the power, that will be 10 to the power negative 10 meters. The ultraviolet, that will be 10 to the power negative 8 meters. Visible light, instead of reducing by 2, now visible light, this is where you find the 7 colors of the rainbow. So you can find all wavelengths from 4 times 10 to the power negative 7 meters up to 7 times 10 to the power negative 7 meters. So 4 times 10 to the power negative 7 meters is the same as 400 nanometers. 7 times 10 to the power negative 7 is the same as 700 nanometers. So from 400 to 700 nanometers, that is in the region of the visible light. And then infrared, the wavelength is 10 to the power negative 4 meters. Microwaves, the wavelength is 10 to the power negative 2 meters. And then radio waves can range from 1 to 10 to the power n, where n is a positive integer. It can be 10 to the power 10 meters. So that will be the wavelength. So if they give you just the wavelength, you should be able to tell which region of the electromagnetic spectrum is given. Or they can even give us the frequency. So we know that all these travel at the same speed, that is the speed of light. And we know that v, the speed, is given by wavelengths times the frequency. So if we know that they travel at the speed of light, that is 3.0 times 10 to the power 8. So we can calculate the wavelength. If you've been given the frequency, you can calculate the wavelength and tell which region of the electromagnetic spectrum that is. Thank you so much for watching this video. Have a blessed day.